going to look at a vector problem using forces of an incline. So what we have here is we're going to talk about, I'm going to introduce, I'm not going to introduce, I'm just going to review a couple of things about how to set this problem up. So first of all, what we have, let me kind of rewind this just a little bit. What we have here is an incline, and we have an object sitting on this incline. And what we want to do is we want to kind of label all the parts to it. So the important piece here is I want to be able to label these pieces and eventually figure out what each part means and how I can look to label the parts given certain information. So the first thing we can do is label the angle. That's usually the easiest part. The angle of the incline is 16 degrees. And we have three different forces we're going to look at. The first force is a force perpendicular to the ground. This is the force due to gravity. So if they tell you the weight of the object or anything like that, you're looking at this force. Now, this object weighs 3,000 pounds. So what we know is that the force, the magnitude of this force headed straight down is going to be 3,000. And that's going to be important later on when we go to work out some other forces. The next part is you have the force that's perpendicular to the actual plane. This is called the normal force. The other part is the actual force that's pulling the object back down the slope. Since it's up an incline, then that object naturally wants to slide right back down that incline. So there's an amount of force that's required to keep that box either stationary, or the box is going to actually slide back, or we're going to push it forward. So we have to figure out exactly how much force is required, and depending on the question, that's going to change the problem. Okay, so the first question we want to look at is, the first thing I want to talk about is actually what's important about this diagram. And truly what we want to make sure that we note is the fact that we have this little triangle. The triangle that is valuable here is, let me highlight it, it's this triangle here. It's a right triangle. We intended that to be right triangle because if you were to write the normal vector, which is the one, which is this vector, so write normal here. The normal vector and the actual ramp itself are perpendicular. That's intentional because we wanted a right triangle. It's going to make this problem easier. What we're going to do now is we're going to take that little triangle and I'm going to extract it out so that we can kind of work with it a little bit larger so it's not so tiny to look at. Now, important part here is that we know that the angle, 16 degrees, is also at the very top here. So that's going to also be 16 degrees. And that's going to always happen. Your angle of the ramp is going to always be the angle right underneath the object itself. You have similar right triangles. You also have parallel lines and transversals and alternating angles. Is where we get this from. So let's go ahead and let's label this part. So there's my 90. This is my 16. The vector that's headed straight down to the ground. So that means this is the weight vector. That's the actual hypotenuse. That's actually 3,000 pounds of force. So the magnitude would be 3,000. Let's label that there. The question we want to know is how much force would be required to keep this box from rolling backwards down the ramp. So the ramp force would be here. So if we label that as X, that's going to tell me how much force is required to keep that box in place. Okay, it's to keep it from moving. And if you've got this labeled, then you're pretty much done. The other question I could ask would be, what's the normal force on the object? And that would simply be to find that component. Now we're only interested in finding the actual force required to keep the box from sliding back down, so we're going to set this up. We know that we're going to use the 16, the X, and the 3,000, so that puts us in a SOHCAHTOA scenario. So we have sine of 16 equals the opposite over the hypotenuse. So once I set that up, I just solve for X, and we're going to get 3,000 times the sine of 16, which is going to equal approximately 826.9. And that would be in just pounds. So you're looking here at the force required is 826.9 pounds, which turns out to be, if I just highlight the arrow, it's this arrow that we found, which is parallel to the ramp. So that's how we know that it's the same. And that's really all you would have to do to find this. Now, I could ask you for y, and in that case, we would end up using the cosine and do the problem pretty much the same way. Or, technically, because I have a right triangle, I could use the Pythagorean theorem to find y. So either way, I could find that normal force. So make sure that you know how to set this little triangle, or this little diagram up. And if I ever give you an example where it's a object sitting on a ramp, you know, this is going to be kind of the method that you're going to want to take to solve these kind of problems.